Polarity in bonds and polarity in the molecule itself are two totally different things. And the lesson today was strictly on the differences and how to use these guys to predict bond polarity and to use them to predict molecular polarity. Okay, that signals the beginning. So this is the lesson for December 11, 2013. Polarity in bonds means that electronegativity is going to be making the difference if we're talking about bonds. Now, we can look at electronegativity tables, like we have on page 169 of our textbook, or we can simply use this little chart, and especially we want to use the trend chart to be able to figure out how big the polarity is, or really I should say how strong the polarity is. Now, a polar molecule is simply a molecule that acts like a magnet because he has a negative and a positive end. So, at any rate, this little guy right here should be familiar to you, and this will help you with the magnitude of the bond. And as you can see over here, ionic bonds, this guy, a difference of 1.7 in electronegativity means that we have a 1.7 means the ionic type of a bond. In these two columns, we have covalent and polar covalent. And we'll figure out how that works in just a second. So it's all based on the difference in electronegativity. And if there is no difference, such as an oxygen ion, not ion, but an oxygen molecule has two oxygens. Because these are both the same atom, this is a non-polar molecule because this oxygen and this oxygen are pulling on the electrons in the middle with exactly the same force. However, when you get a molecule like this, you get these weird little dudes out here, which are simply stating a partially positive and a partially negative on this end, positive on this end. This partial negativity means that we wind up with a polar bond, and the stronger electronegativity is what's going to determine which end is negative. And that'll be important later, but not immediately. So, understand that these little guys are the Greek letter delta. And it simply is a Greek letter delta is what they use for a partial, what we call a partial charge. So, let's move on and see a couple of examples. Well, yeah, we did the examples. Here they are. Yeah. So here's your nonpolar and here's your polar. Now let's go on to molecules. This is going to be really simple because it's based on shape. And shape means the difference will be everything to do with the shape of molecules. And that's why we did shapes in our little lab where we decided what the shapes of molecules would be. So let's look at this little page right here is in tonight's homework, and you can see the link for it there, as well as the link for that first page. So on this page, we're just doing a review now of what we did in that first part, and that is that if two atoms are different, we are going to have a polar bond. So this is strictly for bonds. So polarity between bonds, if the two atoms are different, it's going to be a polar bond. It's so easy. So HBr, as you could probably guess, that's going to be a polar bond. Now nonpolar is if the atoms are the same, and I gave you examples in the last part, but let's do a couple again. If I did chlorine, since chlorines are both the same, this molecule is going to be nonpolar. And for fluorine bips around in pairs like this, and so each fluorine has the same electronegativity, so this too would be nonpolar. So let's move on now and go to shapes and molecules. That's where things are going to get that a lot of people missed today because we didn't have enough time in class to go through it. So here we go. Shape. A linear shape only has, if it has only two atoms, is always going to be polar if the atoms are different. A nonpolar molecule if the atoms are the same. So this line is almost identical to what we had up here with the polar and nonpolar bonds. So the bonds are essentially the whole molecule in this particular instance. Now if we have a linear with three atoms, the outside atoms being different is what makes it polar. And they'd be different because they would be, if they are different, they would have different electronegativities. And so that with just one central atom and an atom on each side, this kind of linear is going to be determined in the same way that this kind of linear will be. Only it's the outside atoms now. Okay? If the outside atoms are different, we are the same. I'm sorry. If the outside atoms are the same, we have a nonpolar. If the outside atoms are different, we have a polar molecule. That simple. Always going to be polar. Okay? Never, and there's only one exception to that, and that's O3. That dude will be polar. Now as we go down here, you can see trigonal planar. For that shape, the outside atoms, if they have at least two different kinds of atoms as what we call terminal atoms, or the atoms on the outside, this guy would be polar. Outside atoms that are all the same would be nonpolar. And trigonal pyramid, you've got always polar, never going to be nonpolar. So that's a simple one, boy. You always know what that is. And a tetrahedron can be either way. Tetrahedral, if the outside atoms have at least two different kinds or are of two different kinds, this guy's going to be polar. But if they're all the same, it's what we call symmetrical. And symmetrical molecules, if the atoms are all the same, you're going to have a nonpolar situation. And now let's look at the shapes and relate them back to what I just told you. Okay, for this molecule, we have a linear molecule because there's only two atoms. Okay, there's a hydrogen and a chlorine. These guys are not atoms. These are unshared pairs. So this molecule only has two kinds of atoms, which makes this, what do you think? Stop the recording and commit yourself, and then start back. All right, if you're back, here we go. This is definitely polar, okay, because the two atoms are different. Now, if we have a linear molecule with three different atoms, these two atoms being the same would make this what? Polar or not polar? And hopefully you got it right. This guy is definitely nonpolar. Where if I take off this chlorine and I put on a hydrogen, now that linear is going to be polar. Okay, because he has the terminal atoms are different. I hope you're looking at your chart because that will help you get into this a little bit better. Okay, just like with the linear, we can have polar or nonpolar with the trigonal plane. Now this trigonal plane has all the atoms the same. So this guy becomes nonpolar because all of even though the bonds are polar because the central atom is different than the terminal atoms, the overall effect of the molecule is nonpolar until we do this to it. I'm going to put a chlorine over here, and now this guy is going to be more negative here than he will be down here because chlorine has a higher electronegativity than does hydrogen. which makes this guy right here the negative end, and these two guys right here the positive ends, because the electrons are shifted in that direction. Now let's go on and do another example. Now here's an example of a bent molecule, and with this guy we have water, red for oxygen and white for hydrogens, and the two unshared pairs. Because of the two unshared pairs, that's what makes him bent, and every bent molecule is going to be polar. So that's an easy one. Trigonal pyramid, always polar, even if the outside atoms are the same. And of course, if I substitute this chlorine for one of these white guys, that will change the center of the charge, but it will not change the fact that this guy is going to be a polar molecule. And then our last dude is the tetrahedral. So for the tetrahedral, you can see any way I turn him, he is going to look the same to you, isn't he? See, I can turn him here, I can turn him here, I can turn him anywhere. Okay, so he's the same everywhere, and this is what we call a symmetrical molecule. I was talking about that when we were looking at the chart, and you have it. If I changed out chlorine, what do you think is going to happen? We change out a hydrogen, for this chlorine. You know what's going to happen. That guy's going to become polar. And that's it, folks. I hope this helps you understand this stuff. And I hope you find this a little bit easier to deal with than you would the stuff in the book. Don't get all upset by those little squiggly things that are the Greek letter delta. They're just a way to show you that it's a partial charge. Have fun. Okay.